But you are not audible, ma'am. Aparamita, ma'am.
Hello.
Yes, ma'am.
Yes. Yes. Am I audible?
Yeah, you are audible, ma'am.
Hello. Am I? Okay.
You are audible,
Okay.
ma'am.
Thank you. Okay. Okay. Yes. We have been assigned MCH 003, and today will be the introductory class. Where we'll be discussing electromagnetic radiation and then a brief introduction to UV spectroscopy. So, a brief introduction to myself. I'm Dr. Apramita Chand. I've completed my PhD from IIT Bhubaneswar. I'm teaching spectroscopy classes as so I'd just like to know before we start about your basic idea of electromagnetic radiation. So now let us not make it a very boring class. Let us start off with interactions. So I'd like to know from you what is your idea of electromagnetic radiations and how they are different from other radiations. Now for this particular course, I would advise that our format be more a little bit of presentation, question answer, or would be solving some questions from previous years. Okay. So during the course of our interactions, I would actually be telling you what are the questions from this particular questions which have been coming in IGNOU exams from previous years. So we can get an idea of how to approach these questions properly, right? So you can either chat in the chat box. You can write, or you can just unmute yourselves and start talking about the concept of electrician, how they are different from other radiations. In fact, in previous year's questions, there was a question: how are electromagnetic radiations different from sound waves? So let us approach the topic from this viewpoint. So any one of you can unmute yourselves and you can start talking, or you can type in the chat box as well. Anyone? Anyone can just so have a little as well. So essentially, magnetic radiation is a form of energy.
Like, uh,
You? Yeah. Please.
yeah, ma'am. Good evening. Actually, in case of electromagnetic radiation, it says both electric and magnetic field, and it's acts in a perpendicular way, like in sine curve, like progressing, and is in
Okay.
perpendicular electric field and magnetic field. But in case of other like sound and other wave, it's a single wave is there. There is not the
Right.
electric and magnetic field both not present there. Only single wave is there.
Right. So very good. That is a indeed a good concept, introductory concept. So these kinds of radiations, they are essentially produced by oscillating electric and magnetic disturbance, right? They are produced by oscillating electric and magnetic disturbance, and also by the movement of electrically charged particles traveling through vacuum or matter. As the participant said very astutely, the electric and magnetic fields, they come at right angles to each other. Okay, they come at right angles to each other, and the combined wave, it moves perpendicular to the oscillating fields, right? The wave actually moves perpendicular to the oscillating fields. Now this electromagnetic radiation, what is it composed of? Anyone? What is it composed of? What is it composed of?
It is composed of photons.
Yes, exactly. So these kind of radiations, they have dual matter. Okay, dual nature of radiation. You must have all heard of in your different 12th class. Even you will have heard of this. Even in your graduation, you must have heard about the dual nature of radiation. I think you should also do a little bit of background reading about how the dual nature of radiation came to be discovered. For example, have you all heard of the de Broglie concept?
Yes, ma'am.
Yeah. So the de Broglie concept you will read about. Then you will go back to how black body radiation was discovered and what were the implications. Just make notes as I tell you. So these are the small bits of background reading that everyone expects you to just know, because not everything will come exactly from the syllabus. Like sometimes it also depends on your logic and whatever you have learned from your previous classes. So de Broglie concept, black body radiation, how did electromagnetic radiation be identified as having dual nature? Okay, so this is a kind of question that can come. So yes, so as coming back to our original question, what is it composed of? This radiation is released as photons. Now what are these photons? They are bundles of light energy. Okay, they are bundles of light energy and they travel at the speed of light. Now do they just normally travel at the speed of light, just randomly like that? Of course not. So now these photons, they are traveling as quantized harmonic waves. Okay, these photons, they are traveling as quantized harmonic waves, and most of the electronic radiation, they can travel through empty space, while if you consider any other kind of waves, they must travel through some sort of substance. So now coming back to our original question, how is electromagnetic radiation different from other kinds of radiation or other kinds of waves? For instance, sound waves. So this was a previous year question. How is electromagnetic radiation different from sound waves? So electromagnetic radiation, because they're caused by electric and magnetic fields, they do not require any medium of transport. Okay, they do not require any medium of transport. But in case of sound waves, they would either need a gas or a solid or a liquid to pass through in order to be heard, right? In order to be heard. Also, sound waves travel around 300 meter per second, whereas electromagnetic radiations, as they are composed of photons, they travel at the speed of light, which is much higher. Also, this speed is always constant. Okay, this is an important fact. In electromagnetic radiation, the speed of light is always constant. But in case of sound waves, because they're medium dependent, they will always be a little different according to the medium, right? They will always be a little different according to the medium. Now, if you have a wave, you must have some of its characteristics, right? So what are the characteristics of waves that you can think of? Just imagine a wave and think, what kind of characteristics can a wave have? Can you type some of the properties, or you just say some of the properties of a wave?
Yes, so, wavelength, frequency, amplitude, etc.
Very good. Very good. Thank you, Divyendu. So yes, so there are some characteristics of waves. If you see a wave, it's like we have a crest and a trough. We all know that from our school time. So amplitude is the distance from the maximum vertical displacement of the wave to the middle of the wave. Okay, so it is basically the height of the wave. This is one important characteristic of a wave, any wave. Also, wavelength. Now what is a wavelength? It is the distance of one full cycle of the oscillation. Okay, it is a distance of one full cycle of the oscillation. Now if you have longer wavelength waves, for instance you have radio waves, they have low energy. So longer the wavelength, lower the energy, so we can listen to the radio without any harmful consequences. But if you have shorter wavelengths like X-rays, they carry higher energy, which can be hazardous to our health. Okay, so shorter wavelength also means greater frequency, and greater frequency means higher energy. So as Divendra told you, you have another characteristic known as frequency. Okay, so now what is the definition of frequency? Anyone? And what is the unit of frequency?
Three
Anyone
of
can
cycles
just
per
tell me?
second. Number of cycles
Yes,
per
exactly.
second. And
Yes.
unity
So
hertz.
frequency is defined as number of cycles per second. Okay, frequency is defined as number of cycles per second and is expressed as either second inverse or hertz. Okay, so how is frequently related to energy? Can anyone tell me the equation?
E equals to H nu. H nu.
Yes. So frequency is directly proportional to energy. Okay. Frequency is directly proportional to energy and is expressed in terms of the famous equation E is equal to H nu, where E is the energy, nu is the frequency, and H is the Planck's constant. What is the value of Planck's constant? What is the value of Planck's constant? H is equal to 6.626 into 10 to the power minus 34, right? That's the value of Planck's constant. Okay, now another two characteristics can be the period and the velocity. Okay, period is the amount of time a wave takes to travel one wavelength. Okay, period is the amount of time a wave takes to travel one wavelength. So its unit is again seconds. Okay, its unit is seconds. And velocity, what is a velocity? Velocity for an electromagnetic wave in vacuum is 3 into 10 to the power 8 meter per second, which means it's essentially the speed of light. Now, these characteristics, although we have learnt about them in detail in school, but even these terms came in a previous year question paper where it was shown that the students had to describe all the terms individually with diagrammatic representation. What is wavelength? What is frequency? What is wave number? Okay, all the diagrams, amplitude with units. Okay, with units. So units are very, very important when you're describing the characteristics of an electromagnetic radiation. Okay. Also, can anyone tell me the relationship between wavelength and frequency? Can anyone tell me the relationship between wavelength and frequency? Anyone can just say?
Inversely proportional. Yeah.
Yeah, but what is the exact equation?
Nu is equal to C by lambda. Nu is equal to C by lambda.
Yes. So, yes, as you said, mu is equal to C by lambda. So, through that, if we are trying to find out the expression for energy, what would be the expression for energy be?
Yeah, E is equal to HC by lambda.
Exactly. So in this type of problems also where we have E is equal to hc by lambda, in some cases they will give you to calculate the energy of a wave if they have given you the wavelength. Okay, they will give you the wavelength. So you know the lambda, right? So in one question paper it was given, calculate the energy of an electromagnetic wave which has wavelength is equal to 500 nanometers. Okay. So if you are given such a question, can you attempt it? Can you attempt it? Type a yes. Type
Yes,
a
ma'am.
yes if you can attempt it. Okay. So you have H value, you have the C value, and now you have the lambda value as well. Okay. So you can easily calculate the energy, but be very careful about what you are writing in the units part. Okay. Be very careful about what you are writing in the units part. Just 1 second. Right. So what are the kinds of radiation types that we know of? What are the kinds of radiation types that we know of? Anyone? What are the waves that you know till now? Types of waves? Okay, I'll give you one hint. First, you can talk about radio waves. Okay, radio waves. Now, radio
Infrared,
waves. Yes, radio
infrared,
waves.
gamma rays,
Sorry, gamma rays. Yes, and
X-ray, UV,
X-ray, UV. Yes, and
Microwaves.
microwaves. Very good. IR, infrared radiation. So, do you know all the regions of the spectrum? Do you know? Are you aware of all the regions of the spectrum?
award, but not reminding me.
Okay, so this is one thing that you will have to just brush up on. All the regions of the spectrum for different waves, along with the wavelength of each, the frequency of each, the energy range of each, everything you will have to just memorize. Okay, so I'll be sharing my screen just now so you can see these. Just 1 second. So anyone can tell me what microwaves are used for? Can anyone tell me what microwaves are used for?
Cooking purpose.
Okay, cooking all also
Telephones.
for remote sensing. Okay, another application of microwaves is for remote sensing. They're usually measured in centimeters. They're used in Doppler radars and they can predict the weather forecasts. Okay, they can also predict the weather forecasts. Similarly, for radio waves, it's usually used for radio broadcasts, TV broadcasts, even cell phones, and they have the lowest energy levels. They're used in remote sensing and also to predict weather patterns. IR, you already know, they collect the thermal energies. So, different types of functional groups in molecules also. So, they can detect what kind of functional groups are there, IR radiation. It's used extensively in analytical chemistry. Okay, similarly for UV visible spectroscopy is also used in determining different kinds of electronic transitions and determining the structural composition of the sample that we are provided with. Okay, they are so they are all different types of applications, and these also come very frequently in exams. So they can just give a brief questions, like in your question pattern you usually have 5 questions, okay, of 15 marks each, right? You usually have 5 questions of 15 marks each, and the first question that has 5 or 6 short questions, they are of 3 marks each, right? So the rest of the questions are usually long answer questions, 5 marks each. For question number 1, you have to attempt 5 questions which are of 3 marks each. So in all these bit type questions, they usually give the questions like this kind of thing, like what is the use of UV spectroscopy, give 2 applications of IR spectroscopy. Okay, so all of this will be given to you. So you have to also apply some of the common sense, like what are the applications, some 2-3 applications you should definitely know. Okay, you should be prepared for with that. Okay, anyone knows the mathematical description of a wave? Does anyone know the mathematical description of a wave? Anyone knows the mathematical description of a wave? Anyone was saying like something about a sine wave? Someone
Yes,
was
ma'am.
saying something about a sine wave.
Yes, ma'am.
So, sine wave. Sine wave. So what is the description? How will you write the equation? How will you write the equation of a wave? So if you were to write a description of a wave, the mathematical equation would be y is equal to a sine kx minus omega t. Okay, y is equal to a sine, and kx minus omega t will be in brackets. So a sine kx minus omega t. What is a? A is the amplitude. What is k? K is the wave number, and x will be the displacement on the x-axis. Okay, x will be the displacement on the x-axis. Now k is equal to 2 pi by lambda. Okay, k is equal to 2 pi by lambda. Right? You're all familiar with these kind of things? I'm assuming you're all familiar with these kinds of things?
Yes, ma'am.
Okay.
Yes, ma'am.
Yeah. So what is angular frequency? What is angular frequency? Anyone can say what is angular frequency? What is the equation for angular frequency?
Ma'am, 2 pi by t.
Sorry, 2 pi by t.
2 pi t. Omega equals to 2 pi by t.
Okay. Yeah. So 2 pi nu or 2 pi by t. Okay. 2 pi nu or 2 pi by t. So where nu is the frequency, right? Nu is the frequency and t will be the period. We have discussed about period earlier. It is the amount of time for the wave to travel one wavelength. Okay. It is the amount of time for the wave to travel one wavelength. Okay. Now Okay, sorry for the interruption. So there was some network drop, and thank you all for staying. So yeah, I'm going to share my screen. I think I can be able to see. Yes. So can you see my screen now? Can you all see my screen?
Yes, ma'am.
Okay. So as we've all discussed, so now we are going to just go quickly because we have discussed a lot of concepts already. So spectroscopy is essentially the branch of science that deals with the study of interaction of electromagnetic radiation with matter. So now we have been discussing a lot about electromagnetic radiation. So we are also going to discuss how it interacts with matter, right? So we have already discussed that electromagnetic radiation consists of photons and that they consist of oscillating electric field and magnetic fields which are perpendicular to each other. So here is the visualization. So if anyone asks you to have a visual representation of an electromagnetic field, you will first draw this diagram. You will show that the electric and magnetic fields are perpendicular to each other. You will also show the amplitude. So now this will be your amplitude, the maximum height, that will be your amplitude. You will say that these are the crests, these are the troughs. Okay, so you can label these kind of diagrams. And of course we have discussed about the different types of characteristics of the waves, like frequency, wavelength, right? And also the relationships between wavelength and frequency we have defined. As I was telling you, the electromagnetic spectrum here is very important because you have to clearly know from gamma rays to radio waves what kind of wavelengths are there. So you will have to remember the wavelength, the frequency, and the energy ranges. Okay, because anytime they might ask you a question about UV visible or IR or microwave, where you'll be asked to also share, write the energy range of this and this radiation, or the wavelength range of this and this radiation. So you should be prepared with the electromagnetic spectrum ranges. Okay, what are the different kinds of radiations, what are the different components of the electromagnetic spectrum, what are the wavelength, frequency, and energy ranges. Okay, so you will be prepared with these. I'll also be sharing some of these slides so that you can just quickly go through while you're preparing along with your study material. Okay, similarly for your visible light, you will also have to remember the patterns. Okay, the patterns, the dispersion. This is a very famous experiment, the prism splitting of white light into different components. So you will also have to remember which one comes out first, okay, which one comes out last, which has a longer wavelength, which has a shorter wavelength. So this is also something that you will have to remember. So what is the basic principle of spectroscopy? Okay, what is the basic principle of spectroscopy? So essentially it is based on the measurement of a spectrum of any sample. What will that sample contain? It will contain some atoms or molecules. Now what is a spectrum? It's a graph of intensity. It's a graph of intensity. Intensity of what? Either the absorbed radiation or the emitted radiation by the sample versus the frequency or wavelength. Okay, versus the frequency or wavelength. And of course, to measure that spectrum, you will require an instrument, and that is your spectrometer. Okay, that is a spectrometer. Now, a very popular broad kind of spectroscopy is your absorption spectroscopy. A very broad definition, a broad kind of spectroscopy is your absorption spectroscopy, where here the sample is absorbing electromagnetic radiation and something is happening. Okay, something is happening. Now what is that something? After the absorption of electromagnetic radiation, what something can happen? Either within the molecule the electronic transitions can occur. If the electronic transitions can occur, that is your UV spectroscopy. If the rotation of the molecule is affected, if the molecule starts rotation, also the rotational energy levels are affecting, then that is your microwave spectroscopy. Similarly, if you have a vibrational structure within the sample, if the vibrational structure is perturbed, if the molecules are undergoing transition between different vibrational levels, then that is your IR spectroscopy or vibrational spectroscopy. So this is all about what happens to the molecular structure, fine structure, on absorption of electromagnetic radiation. And these are the kinds of absorption spectroscopy: UV visible, IR, even microwave. On the other hand, we have a different kind of broad classification of spectroscopy called emission spectroscopy. Okay, called emission spectroscopy. Here, the emission is dispersed according to some property of the emission, and how much that emission was dispersed, the amount of dispersion, is usually measured. And an example of this is mass spectroscopy. An example of this is mass spectroscopy. Now, how does electromagnetic radiation interact with matter? Just let me know. Just let me know how many types of interactions can occur when radiation interacts with matter. Just imagine a light. Okay, a light wave falling on some matter. What will it happen? It can get reflected, right? It can get refracted, it can get diffracted, it can get scattered. So many things can happen if a radiation is interacting with matter. It can also get absorbed. After the radiation is absorbed, some amount will be also transmitted. So many phenomena can be there. So if a question comes in how many ways an electromagnetic radiation is interact with matter, you can give this example and you can write it can get reflect. You have the phenomena of reflection, refraction, diffraction, scattering, absorbance, transmittance. Okay, all of these things can happen. In a previous year question also, they had asked a 3-mark question on describe reflection, refraction, and diffraction. Okay, so all these terminologies you should be familiar with. How are they different from each other? Okay. Pardon. Now, as we've discussed in absorption spectroscopy, in UV visible spectroscopy, what is happening? We have talked about electronic energy levels. Now, what is this electronic energy levels and how are they behaving when they're absorbing the UV visible light? Okay. Now, we have come a little to UV visible today. So at room temperature, usually the molecules are in the lowest energy level. Now let the lowest energy level be E0. Okay. Now, when the molecules are absorbing this light from the radiation, one lone pair or outermost loosely bound electron, they are getting promoted to higher energy states. Okay, like E1, E2. Okay, and whenever this kind of thing is happening, this is known as an electronic transition. Okay, this is known as an electronic transition. We already know that E is equal to H nu. Here delta E will be also equal to H nu, where H nu will be En minus E0. Now what is this N? N is any higher energy state. Okay, N is any higher energy state, 1, 2, 3, etc. And the difference in energy is usually from 35 to 71 kilocalorie per mole. Similarly, for vibrational energy levels, what happens? This is the relatively the spacing is smaller. Okay, relatively the spacing between the energy levels are very small. So there is also less number of energy levels than the electronic energy levels. So when higher radiation is absorbed, the molecules are excited from one vibrational energy to another, or that particular molecule will vibrate with a higher amplitude. Okay, it will vibrate with a higher amplitude. Similarly, rotational energy levels. Again, if you compare it to vibrational electronic transition levels, again the spacing is very, very small. So the energy levels are also quantized and discrete. So now this order is very important. Delta E rotational less than delta E vibrational less than delta E electronic. So if someone asks you the difference between electronic, vibration, and rotational energy levels, how are they different from each other, and what is the how is the spacing between energy levels ordered, you will give this particular order. Okay. Now, if we are coming to UV visible spectroscopy, the very important question which comes again and again in analytical question papers for MCH-003 is the Beer-Lambert's law. We are well aware of it. Okay, we have learned about the definition. We might know about the equation as well. But when it comes to solving problems, many people make mistakes, particularly when the units are getting mixed up, the orders of the things are getting mixed up. Okay, so you need to be very careful in approaching the question. I'll tell you some questions which have been coming from the last 10 years. They have even come in 2020, 2022. Okay, they're as recent as this. Define Beer-Lambert's law, one question. What are the uses of Beer-Lambert's law? Another question. What are the deviations from Beer-Lambert's law? Another question. I will also be solving some, giving you some problems to solve based on the equation. So two problems we will solve, very similar to each other and very easy as well. Okay, so we'll learn more about this Beer-Lambert's law. So let us see what it is. So we already know that Beer-Lambert's law is A is equal to epsilon. Here it is written BC. Many for many other books, if you refer, it will be ELC. Okay, path length is usually, you can give anything. Here they've given B, but you can also write it as L, small l. Okay, so A is the absorbance. Okay, A is the absorbance. Epsilon is the molar absorptivity. Okay, epsilon is the molar absorptivity with units of liter per mole centimeters. L or B is the path length of the sample, that is a cuvette, whatever you're taking the sample, that container, there is a cuvette, it is the path length of the sample. And C is the concentration of the compound in the solution. Now that is expressed in moles per liter. Many cases you will also see it moles per dm cube. Okay, many cases you will also see moles per dm cube. So now before we come to electronic transitions, let me just give you some problems. You will solve them at your home, but these are from previous year's questions. So that is why I'm interested to just tell it to you so that you will solve and keep at your convenience. Okay, so just write calculate the absorbance, calculate, just wait 1 second. Calculate the transmittance when the molar absorptivity is, calculate the transmittance when the molar absorptivity is 2 into 10 to the power 4, 2 into 10 to the power 4 centimeter inverse mole inverse dm cube. Okay, see the value again. Molar absorptivity is 2 into 10 to the power 4 centimeter inverse mole inverse dm cube. Okay, the path length of the cuvette is 5 centimeter. The path length of the cuvette is 5 centimeter, and it contains 2 into 10 to the power minus 6, and it contains 2 into 10 to the power minus 6 mole per dm cube of solution, and it contains 2 into 10 to the power minus 6 mole per dm cube of solution. Okay, this came in 2019. Similar question in 2020 again it came, okay, where they have just changed the values. So the molar absorptivity instead of 2 into 10 to the power 4 was 3 into 10 to the power 4. Instead of transmittance, they asked to calculate the absorbance. Okay. Similarly, the path length was changed from 5 centimeter to 2 centimeter, and the concentration of the solution was changed from 2 into 10 to the power minus 6 to 5 into 10 to the power minus 6. So a little tweaking of values will be there, but essentially the framework of the questions will not be very complicated. But you have to be careful about the units. Okay, you have to be very careful about the units. So if it is there in dm cube, you have to maintain dm cube. Okay, you have to maintain dm cube. Now, another, so all of you have written. Just give me a yes if you have written. Just give me a yes if you have written.
Yes, ma'am.
Okay, right. So next, different kinds of questions also come from electronic transitions. They say draw energy levels and all the possible transitions for organic molecules within a sample. Okay, different kinds of transitions. What are there? Electronic transitions. So let us just explore a little more about it.
So these are the kinds of transition that can happen. Okay, the possible electronic transitions are sigma to sigma star, pi to pi star, n to sigma star, n to pi star, sigma to pi star, pi to sigma star. Now many of these transitions are allowed and some of them are forbidden. Okay, some of them are forbidden. Now let us talk about sigma to sigma star transition. So what is the star? Star represents an antibonding orbital. Okay, star represents, an antibonding orbital. Here, the sigma electron from an orbital excited to the corresponding antibonding orbital, and a large amount of energy is required for the transition. For example, if you have a sigma bond, in methane you have only sigma bonds, CH bonds are there. Okay, so it can undergo a sigma to sigma star transition, and the absorbance maxima is shown as 125 nm. If you have a pi to pi star transition, now pi bonds are found in multiple bonds where compounds have multiple bonds. Okay, like alkene, alkyne, carbonyl, nitrile, aromatic compounds. So they undergo pi to pi star transition. So alkenes generally absorb in the region 170 to 205 nanometers. So here the pi electron in the bonding orbital is excited to corresponding antibonding orbital, pi star. Now, what happens in case of N2 sigma star? Now, N here means the lone pair, non-bonding pair of electrons. Okay, wherever you see an N, you think of non-bonding. When we think of non-bonding, you think of elements which have lone pairs. Now, which elements have lone pairs? Oxygen, nitrogen, sulfur, halogens, right? So, they are all having lone pair of electrons, and they require less energy than sigma to sigma star transitions. Obviously, because in a sigma bond, the bonding is there. In the lone pair of electrons, they are just held loosely, they are not bonded, so obviously they require less energy. And also the number of organic functional groups with N2 sigma star peaks in the UV region is a little small. Okay, now N to pi star transition, the electron from the non-bonding orbital is promoted to antibonding pi star orbital. Just give me a second. Yes. An electron from the non-bonding orbital is promoted to antibonding pi star orbital. Now, when we talk of N to pi star now what is happening here? The double bond will be there, and also some kind of element will be there which has a non-bonding electron. Okay, it has a non-bonding electron. So here we will have heteroatoms. Okay, heteroatoms will be there like oxygen, nitrogen. Okay, so C double bond O, C triple bond N double bond O. So lone pair will also be there, double bond will also be there. And they require the minimum energy. Okay, they do not require much energy, and they show absorption at longer wavelength as well. Now we talked of some forbidden transitions. Okay, like sigma to pi star, pi to sigma star. These are only theoretically possible. Okay, sigma to pi star and pi to sigma star will require a lot of energy, and so they are not favored, they are forbidden transitions. N to pi star and pi to pi star, these show absorption in region above 200 nanometers. And this region, the region above 200 nanometers, is accessible to a traditional UV visible spectrophotometer. Okay, it is accessible to a traditional UV visible spectrophotometer. So if you are asked to draw a graphical representation of electronic transitions, you can draw it within like this. Okay, sigma to sigma star will take the highest amount of energy, N to pi star takes the least one. Okay, N to sigma star is there, pi to pi star is there. Now these two you can just write pi to sigma star and sigma to pi star. You will put a label here that these are forbidden transitions. Okay, these two, pi to sigma star and sigma to pi star, they will be theoretically possible but not favored. Okay, so this is a diagram that you will have to remember. So this is a generalized molecular orbital diagram where you are showing the possible electronic transitions. You will draw the diagram, you will label them, you will also in your notes you will write. In the exam also, if they ask to draw graphically after the graphical representation, I'll prefer if you write like what are the kinds of molecules which exhibit these kind of transitions. Okay, you can write that for better marks. A few general terms in UV visible spectrometer. spectroscopy? Chromophore. Okay, chromophore is a general term. What is chromo? Chromo means color. Okay, chromo means color. So anything that will impart color, they are known as chromophores. And if you have multiple bonds capable of absorbing radiations above 200 nanometers, like NO2, NO, CO, CN, okay, anything with double bonds, they will impart more amount of color. Okay, they will impart more amount of color. Now, what are oxochromes? If chromophore is enhancing the color, oxochrome is enhancing the intensity. Okay, it modifies the ability of the chromophore to absorb light, and it alters the wavelength or the intensity of absorption. Okay, so usually if you have a functional group with non-bonding electrons, it acts as an oxochrome when attached to a chromophore. Okay, it will alter the wavelength and intensity of absorption. For instance, this is a chromophore. Okay, benzene is a chromophore because it has multiple bonds. Now if you're attaching some species like OH and NH2, okay, which have non-bonding electrons and can also be conjugated with the ring, it can alter the wavelength or the intensity of the absorption. So phenol and aniline will both have longer wavelength of absorption. Okay, so this is how the functional groups are acting as oxochromes. Now, can absorption and intensity shifts happen, and when do they happen? Okay, these are the 4 kinds of things that can happen when the shift is happening in a intensity. So it can be bathochromic shift, hypsochromic shift, hyperchromic shift, or hypochromic shift. Okay, now I want you to write some notes about each of these shifts. Okay, extensively for this particular presentation, we might not discuss that extensively, but I want you to write more about these kind of shifts and the examples. So this can be an assignment. You can just go and find out in what cases the bathochromic, hypsochromic shifts occur. These are concerned, the first and the second cases are concerned with the change in wavelength. Okay, they're concerned with the change in wavelength. Well, the third and the fourth term, the hyperchromic and the hypochromic effect, they are concerned with the change in intensity. Okay, that is why the intensity shift and as well as the absorption shift. So the first 2 are absorption shifts, the second 2 are intensity shifts. Okay, so in red shift, as you can guess from here, the absorption is shifting to longer wavelength. And if you have an oxochrome or if you are changing the solvent, this kind of thing can happen. You have already seen in case of phenol, the longer wavelength shift happened because of the oxochromic groups like OH. Okay. Similarly, you can have this example of a paranitrophenol. You can be asked examples here as well. Like in alkaline medium, why paranitrophenol gives longer wavelength? Because once the negatively charged oxygen is there, it will delocalize more effectively than the unshared pair of electron. Okay, so this can be an example. Similarly, hypsochromic shift refers to a shift towards shorter wavelength. Okay, so any kind of group which will remove the conjugation, okay, remove the conjugation, that will cause your blue shift. Okay, so for example, if you are having a basic group like aniline, so aniline, what happens? The shared pair of electrons of nitrogen, they conjugate with the ring. But if you're adding an acidic medium, this kind of salt is formed, NH3 plus Cl minus, so the conjugation is lost. So that is why a hypsochromic shift or a shift towards shorter wavelength is formed. Similarly, if, as I've already told you, intensity shifts, if the absorption intensity is increased, it is hyperchromic. For example, if you are introducing an oxochrome, then the intensity is increasing from pyridine to 2-methylpyridine. If you have hypochromic, if you are having something like this, the absorption intensity is decreasing. Okay, the absorption intensity is decreasing because the conjugation of 2 rings is decreasing, then it is a hypochromic shift. So that here the intensity is decreasing. So these are the intensity shifts. So this is how you represent in a graph. If you are asked to represent in a graph about shifts and effects, you will write about this: absorbance versus wavelength graph. If you go towards the higher wavelength, then red shift, lower wavelength blue shift, ऊपर जाओ तो hyperchromic shift, नीचे जाओ तो hypochromic shift. Okay, because here the absorbance is varying. Here the wavelength is varying. Okay. So what are the basic principles of UV visible spectroscopy? First, you have to see the ranges. Okay, you have to see the ranges. What are the ranges for UV? What are the ranges for visible? Visible, we all know it extends from 400 to 800 nanometers. In UV also, you have two kinds of regions, near UV and far UV. Near UV is from 200 to 400, far UV is below 200. And this far UV is usually studied under vacuum conditions. What are the kinds of solvents? Now, when you're studying principles, you will study what are the kinds of solvents used, what is the kind of instrumentation used, and this kind of instrumentation is a very frequent question in your question papers, okay, where you are asked to describe the working of the instrument, the function of each component, and how it is used subsequently. So instrumentation, let's see what are the components of a UV visible spectrophotometer. So you have a source. In any spectrophotometer, you will have a source, you will have a sample compartment, you will have a detector, you have a record. This is a very basic. So even if you don't have any idea and if you're just writing, you will write these 5 components for sure. You must have a source, you must have a filter, you must have a sample compartment, a detector, and a recorder. But the sources, the detectors, the kind of sample compartments, these will differ from spectrophotometer to spectrophotometer depending on which radiation you are seeing. So simple UV visible spectrophotometer you can represent this way. You can have a source. How will you put the radiation? So there'll be a slit, there'll be a dispersing device, then that particular radiation will fall on the sample holder or the cuvette, and finally it will fall on the detector. So this is a very simple schematic diagram. So what kind of components are there? You will have a source which has to be stable source, okay, and it must be stable, it must provide the desired wavelength. So we will choose a source like that. Similarly, wavelength selector, how will you cut that region of the electromagnetic spectrum? You might need filters, monochromators, prisms. Similarly, how will you hold the sample? You must see that it is transparent and that it will be equivalent for any kind of sample solution. It will not react with the sample. Okay, so you must have a sample container like that. Similarly, a detector which will convert the radiant energy into a usable signal, because that is what will be recorded. And after the signal is there, how will you amplify it and send it to a thing that can read the signal and make it human readable format? Okay, so that will be a processing unit. So you have two kinds of spectrophotometer based on the beams. You have a single beam spectrophotometer where you have a light source here, you have a wavelength selector, then it again just directly falls on the sample, detector, and readout. Okay. On the other hand, you have a double beam spectrophotometer. Now the double beam spectrophotometer is a very popular diagram that is asked. It is also asked about the components. It is a very frequent question in your MCH-003. Okay. So now you will have, instead of one beam, you have two beams. Okay. You have two beams going through two different kinds of sample compartment. So here in single beam, you had just the sample compartment. Here you also have a reference cell. Okay. So you will have a source which will fall into two kinds of sources will be there. The light will fall through the reference cell. Here, this will be the sample cell. This will be the blank solution. This will be the sample solution. And the detector will detect both the signals. And the signal difference will be amplified. In single beam, what was happening? Only the sample cell was there. Whatever is the output, it was detecting. Here, it is detecting with reference to a reference blank cell. Here, the results are more accurate because you are doing a zero baseline correction through the reference signal subtraction. Okay, you are doing a subtraction of the reference cell, which is essentially the solvent in which the sample has been diluted. So the detectors are detecting two different signals and the difference is being amplified, and that you are getting as a result. What are the sources of UV visible spectroscopy? Very important question. This had also come in a previous year question paper. What are the sources of UV radiation? So these are the sources: deuterium lamp, hydrogen lamp, tungsten lamp, xenon discharge, mercury arc lamp. Okay, for visible radiation, what you're using? Mercury vapor, carbonon lamp. Okay, so all of these things you are using.
Excuse me, ma'am. Excuse me.
Yes.
Ma'am, again, meter. Again about double beam spectrophotometer.
Okay, right. So in the double beam spectrophotometer, what is happening is you have two kinds of cells, the reference cell and a sample cell. Okay. So reference cell, the light is passing through the reference cell as well as the sample cell. So you are placing two kinds of cell in the compartment. In fact, this is a design that is used in traditional spectrophotometers of today. Okay. So here the detector is used to detect the signal from the reference cell. The signal will also be detected from the sample cell. Finally, the difference between the signals will be amplified. So here you're getting a more accurate result because you're doing a baseline correction. A baseline correction means whatever the environmental effects are that you are negating. So whatever the effects are due to the kind of solvent, anything related to the solvent effect in which the sample has been dissolved, that you are subtracting. Okay, those kind of signals you are subtracting. So you are getting the actual absorbance of the sample and not any artifacts from the solution in which it is dissolved. Got it? Artifacts means,
Okay, ma'am. Thank you. Got it.
yeah, thank you. So light sources, I hope you've all noted down. You'll anyway receive the presentation, so not to worry. But these radiation sources you will have to remember because these are coming in questions. Okay, UV radiation sources, one UV visible radiation, so you can write differently also. Deuterium, hydrogen, this is for UV, and for visible you have tungsten lamp, carbonon lamp, and mercury vapor lamp. So what kind of wavelength selectors are there? You already know we have discussed about filters and monochromators. Okay, two types of filters can be there, interference and absorption. Okay, what are monochromators? Monochromators, they continuously scan a broad range of wavelengths. You can have a prism, you can also have a grating. Okay, this you have learned in physics. In prism, you can reflect or refract, while in grating, you can either diffract or transmit. Okay, transmission type and diffraction type. So they will scan a broad range of wavelengths and only give a few wavelengths to pass through. Okay. Now, sample compartment. Have you all seen a cuvette? Has anyone seen a cuvette? So this is what a cuvette looks like. This is your sample container. इस type of cuvettes में हम लोग sample इतना तक भरते हैं. Solution is usually put in sample containers like this. Okay, and the main characteristic is what? It should be transparent. Okay, it should be transparent, and the geometry should be such that the signal will be maximized. You will see that the sample is absorbing the signal, not that the sample or the construction should not be such that it will scatter too much. If it scatters, then what is the point of absorption spectroscopy? So it should be transparent, it should be non-reactive, it should also maximize the signal. So the geometry has to be constructed that it minimizes the scattering. So there are typical materials that a cuvette is built of. Usually quartz is preferred. Okay, quartz is special. Also an optical glass kind of thing is now gaining traction. Usually quartz is preferred for far UV and IR. Also one special kind of optical glass is also being used in sample compartment these days. Okay. So this was also a question about sample compartment, like why is a cuvette required for the sample compartment? So you will see the three characteristics: that it should be transparent, the geometry should be proper, and that it should be non-reactive. And you can also mention an example. For example, these materials have all these characteristics, so they are used in fabrication of cuvette. Okay, so this is a possible question. Similarly, detectors. Okay, what kind of detectors are there? So three kinds of detectors are there: barrier layer cells, photoemissive cell detector, photomultiplier. Now you just remember the main points. Okay, main points of the various components. Need not go into extensive details. If you write properly point wise, then you will have a long enough question answer that you can write for 5 marks. Okay, but you should know what to write. You should, for example, if you're writing about detectors, you write about what they do, what are the types. Okay, so this is a summary of what we have discussed till now. The region, ultraviolet and visible, the source, one each is there. You can also complete. You have to complete this table. Okay, just extend this table and include all the sources here. When you're writing in your notes, do not just restrict yourself to this. Make sure write all the detectors. Also add a column here about filters. Okay, monochromators, what we discussed, prisms and gratings, that also you can put here. Okay, now this is something that has not been there in your question papers till now, but I would just advise you to note these 6 methods and what they are. Just one line you remember about what kind of other UV visible spectrum photometric methods are there, especially if you're going for multi-component analysis. Okay, this I'm not discussing in detail. These are just different kinds of method, and definitions are given. You need not go into the extensive derivations of this. Just remember the derivations, sorry, just remember the definitions and a one diagram each. So even if you remember 3 or 4, you can write if the such kind of questions come. But you usually with UV spectroscopy, very simple questions come. Usually problem solving questions are coming mostly. So let's just skip this one. Okay. So why is UV spectroscopy used? Also, why, how Beer-Lambert's law can be used. So here you can get some of the hints for characterization of compounds, like conjugated compounds we have seen, aromatic compounds. So you can use it in qualitative and quantitative analysis. You can also use to find out the molar concentration of the solute. Sorry, yes. Yeah, you can also detect impurities. Okay, you can detect impurities in organic solvents. You can detect how many isomers are there, and also how you can find out the molecular weight. Beer's law also finds out the molecular weight. So if you are finding out the concentration, you can find out the molecular weight using Beer's law. If you're looking for reference books, you have your study materials available. I'd suggest that you mute yourself if you're on the way. Okay, so if you're looking for reference books, your study materials are more than enough. So, but for supplementary reading, these are very good books. Pavia is a good book, Introduction to Spectroscopy. You can look into Y.R. Sharma also. These are the basic, like undergraduate level. If you want to go to the very basics, Y.R. Sharma is a very good read and quick read. Okay, easy language. So Pavia is good. You can also refer to Kemp. Okay, I think there's a book called William Kemp. William Kemp is there. Apart from this, Silverstein is there. Silverstein is a very good book for NMR, mass spectrometry. This is very good book for any kind of level. I followed it through my graduation and master's levels. So Silverstein, Kemp, Pavia, Y.R. Sharma, you can also see. If you are going to go for more extensive like chemical analysis, like problem solving, then you can also refer to P.S. Kalsi. Okay, P.S. Kalsi. So here, this is more of the physical kind of spectroscopy. What is the physical significance of spectroscopy? The energy levels. So this deals with that. If you want to go to the organic part of the spectroscopy, like functional groups you're seeing, okay, the problems you're solving, then you will have to consult P.S. Kalsi. That is very good book, fat book, but good book. Okay. So here I will stop and I'll not bore you in the first class itself, but we will have to be quick with the completion of the courses, because the course is quite huge and our time is limited. So you will have to do quite some background reading. I will be fast when we are discussing. but you can always reach out to me with your questions, no issues. Okay. So today we have discussed about different kinds of questions that are coming in previous years. So I whatever questions I had collected, I have explained and we have discussed everything. Uh, Different kinds of variations can come. For example, there was a question like green light has wavelength 535 nanometers, calculate its energy. Very easy, you can do that. Okay. Beer-Lambert's law, very important. Please go through it again and again. Also, construction of the spectrometers, different components. What is the function of each component? What is each component made of? Okay, make that table. If you make that table properly, that last table that I showed, that was just one example. You make the table complete. If you make the table complete, you have it set in your mind and you can write about it. Okay, make sure you know the functions of each. Also, general instruction for all kinds of spectroscopies that we will be discussing, the functions, the utilities, what is the use of this in various applications. That is a question that is coming repeatedly. For IR, I think there are like 5 to 6 questions which are coming for IR spectroscopy. Okay, IR spectroscopy, what are the applications? Even for UV visible, what is the qualitative application of UV visible spectroscopy? How can we use this in analysis? Okay, so these kind of questions are coming again and again. So you maintain points, write bullet points, write the examples, then you will not feel that you have a lot to learn. Okay, so I think we'll be stopping here because let us just assimilate whatever we have learned. I will forward this presentation so that you can have access and you can read in your free time. And tomorrow we will take up two other different types of spectroscopies. Okay, so if you have any doubts, you are welcome to ask here, or you can also, anything relating to the questions also you can ask, or you can also ask me tomorrow. We will do a short Q&A tomorrow before we start. Okay. Yes. Okay. So Yash has a question, I think.
यस मैम। मैम जो ये स्लाइड्स मैम कहाँ पे शेयर कर सकते हैं तो हम लोग उसको पढ़ लेते थोड़ा।
कौन सा वाला?
प्रेजेंटेशन
मटेरियल्स।
मैम। यस मैम।
हाँ हाँ, मटेरियल्स मैं एक बार सर से बात कर लेती हूँ कि कहाँ सेंड करना है। अगर उनको सेंड करते हो आपको फॉरवर्ड कर दे तो दैट विल बी बेटर। ठीक है
मैम
तो
एक्चुअली हम लोग एक व्हाट्सएप ग्रुप भी क्रिएट किए हैं वो लोग, ये जो क्लासेस के लिए।
अच्छा
तो आप
अच्छा, तो मैं सर से एक बार बात कर लेती हूँ कि मुझे कुछ मटेरियल्स भेजने हैं, तो मे बी ही विल गाइड मी और मे बी ही विल ऐड मी टू द ग्रुप। ठीक है, तो यू विल गेट द प्रेजेंटेशन, नो प्रॉब्लम।
ओके मैम।
ठीक है, थैंक यू फॉर कोऑपरेटिंग एंड आप लोगों ने अच्छे से आंसर भी किया है। आई थिंक इट विल बी इजी फॉर यू। आप लोग स्टडी मटेरियल को अच्छे से पढ़ो एंड मेनली हम लोग ड्यूरिंग दिस काउंसलिंग सेशंस, पढ़ाई तो आपको खुद से ही करना पड़ेगा, बट क्वेश्चंस एटलीस्ट प्रीवियस ईयर्स के अगर हम लोग डिस्कशन में रखें तो दैट इज वेरी हेल्पफुल। द लास्ट 10 years के क्वेश्चंस अगर आप अच्छे से प्रैक्टिस करके जाओ, दिस इज गोइंग टू बी रियली हेल्पफुल बिकॉज आई एम एन इग्नू स्टूडेंट माई सेल्फ, so I understand how difficult it is to finish a very large portion. But when we see it in terms of question answer, इस portion से क्या question आ सकता है, then it becomes a little easier. ठीक है, एग्जाम में भी कॉन्फिडेंस आ जाता है. So we'll be discussing these questions and how to approach them. ठीक है, हर portion में से I'll tell you कि उस portion में से क्या question आया था. ठीक है, so it will be easy. Okay, thank you. Let us end this session today. So I'll be leaving. Thank you so much. Bye bye.